All right, let's talk about one of the biggest ideas in backend engineering, distributed systems. Now, I know it sounds super complicated, but I promise you, the core idea is actually pretty simple. It's all about how we get computers to work together as a team, instead of trying to do everything on their own. Let's dive in.
So take a look at this. It might seem like a totally normal, simple server setup, right? But here's the thing. There's a huge vulnerability here that a lot of people miss. It's kind of like a restaurant that has just one amazing superstar chef. Well, what happens if that one chef calls in sick? The whole restaurant shuts down. That's a single point of failure, and it's the exact problem that distributed systems were designed to fix.
And this really brings us to a fundamental choice we have to make when we're building software. Are we going to rely on that one super chef to do everything, or are we going to build a whole professional kitchen team? Let's break down what that actually means.
Okay, first up is the Monolith. This is our super chef. Basically, one single application on one server handles absolutely everything. It takes the order, it does all the logic, it talks to the database, it sends the food back out. And, it's simple to get started with. But what happens when you suddenly get a rush of 100 customers all at once? Well, that one chef gets totally overwhelmed and the whole kitchen just grinds to a halt.
So what's the fix? You build a team. In a distributed system, we split up the work across a bunch of different computers or services. You might have one service that just handles logins, another one that's a specialist at processing payments, and a third that's just in charge of serving up images. It's just like a real kitchen. You've got your grill station, your salad station, your drink station, and they're all working in parallel. And the best part? If the salad chef is out for the day, you can still sell burgers and drinks. The whole system doesn't just crash.
Let's put these two approaches side by side, because this is where the trade-offs really become clear. With that Monolith chef, if you want to serve more customers, your only option is to, give the chef a bigger kitchen and a faster oven. That's called vertical scaling, and it gets expensive fast. With the distributed team, you just hire another burger chef and add another grill. That's horizontal scaling. It's way easier and cheaper. Reliability obviously is way higher with a team. If one computer goes down, the others can cover for it. But, and this is the big one, you've now introduced complexity, right? Managing a whole team is just way harder than managing one person.
Okay, awesome. So we've hired a team, our local restaurant is running super smoothly, and it can handle a ton of customers. But all our chefs and all our customers are in one city. What happens when we suddenly have people trying to order from New York and London and Tokyo? Well, we slam headfirst into a problem we absolutely cannot avoid, the actual speed of light.
And this is our next massive challenge. I'm not kidding. We are literally fighting physics now. No matter how fast your computers are, information still has to physically travel across the globe, usually through these massive fiber optic cables under the ocean. And that travel time, that's what we call latency.
Let's make this real. For a user in Tokyo to get some data from a server in the US, that round trip is going to take about 150 milliseconds. Now that doesn't sound like a lot, but trust me, you can feel it. That is the difference between an app that feels instant and one that feels, laggy and annoying.
Now, look at this. If that same user in Tokyo talks to a server that is also in Tokyo, that time plummets to around 10 milliseconds. Boom. That feels instantaneous. The takeaway here is so clear. We have to get our application and our data physically closer to our users. But how do we actually do that?
So, tool number one in our arsenal is the CDN, the Content Delivery Network. The best way to think about this is like a global network of vending machines. Your main server is the factory that makes the product, things like images, videos, static files, and the CDN stocks copies in vending machines all over the world. So a user in Tokyo just goes to their local vending machine and gets the file instantly. But here's the key limitation. A vending machine can only give you stuff that's already made. It can't cook you a fresh burger. It's only for static stuff.
For the actual thinking part, the dynamic stuff, like logging you in or processing your credit card, for that, we need more than a vending machine. We need a full-on branch office. And that's what a multi-region server is. We take the actual brains of our application and we run a complete copy of it on a server in Tokyo. Now that branch office can make decisions and do real work right there locally, making the whole experience feel super fast for our users in Japan. Okay, but wait. In solving one problem, we've just created a brand new and, honestly, much harder one. If we have a branch office in Tokyo and head office in the US, how do we keep them in sync? If a user in Tokyo updates their profile picture, how does the database back in the US find out about it, and how fast? This is the million-dollar question. Seriously, this problem of data consistency is one of the toughest challenges in all of backend engineering. This whole process of keeping databases in different parts of the world in sync is called database replication, and there are basically two main ways people try to do it.
So, the most common approach is what I call the boss and assistant model. You designate one database, let's say the one in the US, as the boss. It is the single source of truth. Any change to the data, what we call a write, has to go to the boss. The boss makes the change, and then it tells all its assistants around the world, hey, update your records. So reading data is blazing fast, right? You just ask your local assistant in Tokyo. But writing data is still slow, because you have to make that long-distance call back to headquarters.
Now you might be thinking, well, why not just have two bosses? And that's the other model called multi-master. Here, both the US and the Tokyo databases can accept writes. Everything becomes incredibly fast. But you've just introduced a massive risk: data conflicts. What happens if a user in Tokyo changes their name to Bob at the exact same millisecond that an automated process in the US tries to change it to Alice? Who wins? The system has to have a way to resolve that, and it gets really, really complicated.
And this brings us back to that hard reality check: physics. No matter which model you choose, you cannot escape the speed of light. There will always be a tiny delay while that update message travels from one database to another. We call this replication lag. It might just be milliseconds, but it means that for a brief moment in time, your data across the globe is out of sync. Perfect instantaneous consistency is physically impossible.
So this leads us to the ultimate question, right? Given that we have this replication lag, and given that networks can fail at any time, can we ever build a system that is always on, always fast, and always perfectly consistent everywhere? The answer, which has been proven with math, is a hard no. You can't. And that mathematical proof, the reason for that no, is something called the CAP theorem. You can think of it like a fundamental law of physics for distributed systems. It governs every single one of them, and it forces engineers like us to make a really, really tough choice. So, the CAP theorem breaks down into three things we'd love to have in our system. C is for consistency. Everyone sees the same data at the same time. A is for availability. The system always responds to requests. And P is for partition tolerance. The system keeps working even if the network between our servers breaks. And the theorem states, very simply, out of these three, you can only pick two.
But here's the crucial insight. In the real world, network connections fail. Servers become unreachable. These partitions are just a fact of life. They are going to happen. So that P, partition tolerance, isn't really a choice. You have to design for it, which means the real, fundamental choice for every distributed system is between C and A. Do you prioritize consistency, or do you prioritize availability?
And this really boils down to two completely different philosophies. A CP system, one that chooses consistency over availability, operates under the motto, better to fail than to lie. If the Tokyo server can't talk to the main US server, it will just return an error instead of risking showing you stale data. An A-key system, availability over consistency, has a different motto. The show must go on. It'll give you the best data it has, even if it's a few seconds old, because keeping the service online is the #1 priority.
So where does this actually matter? Well, think about your bank. You absolutely demand consistency. You would much rather your banking app give you an error than show you the wrong account balance. That is a classic CP system. But now think about a social media feed. Is it a disaster if you see a post that's 5 seconds out of date? Not really. It's much more important that the feed actually loads. That's a classic AP system.
And that's our journey, all the way from a single chef in one kitchen to a global team of services governed by the laws of physics. So the next time you open an app on your phone, think about this. Think about the trade-offs those engineers had to make. Are they prioritizing perfect, up to the millisecond data? Or is their #1 goal just to make sure the show always goes on? The answer tells you something incredibly deep about how that system was built.